So the main way we talk about the next part of the course, or we introduce it, is with the area problem. Let's start with something that you know. Distance equals rate times time. Okay, so you've been doing that since middle school. And so the question is, what does this have to do with the derivative, the antiderivative, and area? Because that's what this next topic is all about. Well, let's take a look. Let's say we've got a constant velocity of 60 miles per hour. And let's say we're going to go from t equals 2 to t equals 5. How far do we travel? Well, okay. I think most students, certainly AP Calculus students, would look at that and say, 180 miles? But that's too easy. What does that have to do with calculus? Velocity, distance. Think about it. Which one's the derivative of the other one? Right? And so all of this does make sense. And so then you think, well, wait a minute. Have I been doing calculus in the back of the car since I was 10 years old? And the answer is yes, of course you have. Every time you've calculated distance from velocity, you've been doing calculus. You've been doing integration. Every time you've calculated velocity from distance and time, you've been doing calculus. You've been taking derivatives, right? Right? So let's take a look at this. Let's break this down. So here's my t-axis. Here's my velocity axis. Here's v of t equals 60. Here's t equals 2 to t equals 5. Do you notice anything? If I take the area of that rectangle, well, that's 3 times 60. The area of the rectangle is 180. What else do we notice? Well, how did we come up with 180 from here? That was the change in position. The change in position was 180. And as anybody who's been in this class since September will tell you, velocity is the derivative of position or distance. So what do those three things have to do with each other? Well, here now, I'm going to present to you the heart of introductory calculus. In fact, I would go so far as to say that everything that we're going to talk about for the next 2 months is going to have its foundation in the following problem. This is it. This is it. And it's going to be this same problem with a little twist. So if you're ready, you can draw this curve. 2, but instead of 5 now, we're going to call this upper limit x. Oh, so I'm going to start my trip at 2 o'clock, and I want to know if I end at x o'clock, how far will I have traveled? The answer to that question is probably the single most important concept in all of calculus. This is it. You know how sometimes you go to the movies and you have to kind of wait and you see and you don't really know when the climax is going to happen, and then the answer, the mystery gets solved? I'm telling you, what I'm about to do is it. In fact, textbooks call this the fundamental theorem of calculus. This is it right here. So let's do it. Okay? Now, let's use the area formula from geometry. To find the area of that rectangle in terms of x. We have what? 60, the height, times the base. Well, what is this length right here? Well, I knew this length was 3 because 5 minus 2. So this length must be x minus 2. Okay? Now, this gives me 60x minus 120. Now, is that true? Well, let's see. Let's do our previous problem. 60 times 5 is 300. Minus 120 is 180. So this is true for any x value. Wow. It's almost like the 2 doesn't matter. There you go. Now, this means what? The distance traveled in x minus 2 hours is 60x minus 120. Oh. Notice how I went from the velocity 60 to the distance here. And what else do you notice? What is the derivative of 60x minus 120? Think about that for a minute. The derivative of this is 60. Do you think that's a coincidence? Do you think there's a connection between the area under the curve and the derivative? Well, yeah. Especially when the curve is the derivative of this function. But this whole connection, right? From area to derivative, the velocity and distance. This is essentially the fundamental theorem of calculus. I can take the derivative of the equation here to get 60. This equation represents the antiderivative of 60. Wait a minute. There's a connection here. This is what we get to study for the next 2 months. Okay? This is what we're going to study. The connection between little f, A, B, area, and then big F of x. Because we know that big F prime equals little f. And big F prime from A to B represents the area under little f. Now, we certainly don't expect you to fully understand this right now, but these are the thoughts I want you to have in your pea brain as we start working with area. Okay? I want you to always be thinking about the connection between the area under the curve of little f and the connection from that with big F, because big F prime is little f. Whoa. This is your life right here. All right? This is your life. All right. So as we do all these problems now for the next few days, I just want you to keep this in mind. Clear? Okay. Now, let's present a couple of the common questions that we're going to encounter. So, to start with, and this is where most calculus textbooks and introductory calculus courses start, is with the area problem. Okay, so now that I've given you the secret, I want you to not really think about it too much. I just want you to focus on area. Okay, so for example, if we have a nice linear curve, x plus 2, and I want the area from 1 to 5. Can we find that area? Sure. Let's just find it using geometry. The area here, that's a nice trapezoid, and I'm sure all of you remember 1/2 height times the sum of the bases. Okay, not too bad, right? That's 2 times 10, so that's 20. We had the area of the semicircle, right? Oh, that's a bad semicircle. Let's say this is, let's say that's x squared plus y squared equals 4. So that'd be y equals root 4 minus x squared. Okay, this area here, we can find that using geometry, right? So the area is going to be 1/2 pi r squared, or 1/2 pi 2 squared, 2 pi. Okay. So okay. So many times we'll be able to find the area using geometry. What happens when we cannot use geometry? Okay. All right. And the answer here is the rectangle approximation method. Calculus students have been doing this for centuries, and you will do it as well. We are going to use the rectangle approximation method. And I'll show you how that works in the next video. Now, by the way, what if the upper limits here, what if this was not 5 and this was not 2, but this was x? We could calculate the area in terms of x. And then if we took the derivative of that area expression, what would we get? If you think you'd get x plus 2 and root 4 minus x squared, you'd be exactly correct. That's the connection. That's the fundamental theorem of calculus. That's what we're going to build to. So, in about 3 or 4 more videos, we'll revisit this and you'll be able to put it all together. For now, though, I want you to read about the rectangle approximation method, and we'll get to it in the next video.